But the big gain, I think, comes when cars can plan automatically where and when to drive and just pick up and drop people where they need to be, rather than having people owning their own vehicle, parking their own vehicle, and having all these vehicles standing still in city landscapes.
Welcome to a brand new episode of our podcast, Human in AI, Mind Machines in the Gradient Sense.
Thanks that you tuned in again to geek out with us over the fascinating field of AI and the role of the human. We are Uli and Aburi, and we're super excited to introduce you to our today's genius mind, Matthieu Worm, who's the director for autonomous vehicles for simulation and test solutions at Siemens Digital Software. He envisions the future of mobility, not only to be safe, comfortable, and efficient, but also silent and beautiful. I love that. And Matthieu also contributes to that vision with a balanced engineering, business, and user-centered perspective. But I guess that's enough of an introduction, so let's dive right into it. Matthieu, we are super happy to have you with us today. Thanks so much for taking some time to be the guest on our podcast. How are you doing, and where do we catch you today?
Cool, yeah, thanks for the opportunity. And you catch me from home, obviously, in Leuven, in Belgium, with almost a spring-like day with blue skies and nice weather to walk around for a bit.
All right. So I would say let's start with an easy question first, right? Are you a simulation, or are we all part of a gigantic simulation? Any clarifications you want to make?
No. I try to keep these worlds very separate. And even though I'm a big simulation guy already for years, for decades almost, and a big believer in what simulation can bring, I'm still very happy to spend life in the real world. And it makes me think of also what I tell my children, right? That gaming is nice and being in Fortnite is obviously good fun. But that the real world out there is always more important than what happens on the screen.
It's super messy, huh? As well, right?
Yeah, absolutely.
Okay, maybe we should try to make it a little more down to earth, right? So, Matthieu, when will I be able to sum? And secondly, when will we have autonomous cars in the public?
Now, we have them today. It just depends on where you are, right? So there is robo-taxi services active in the US and in China, where people like you and me can order a taxi and be picked up by a self-driving car. In a couple of places, even without safety driver. In a lot more places with a safety driver. But no, autonomous vehicles are there. There's just big regional differences, and especially in Europe, due to the way we work and we organize legislation and safety. It will take a bit more time in Europe before we see these solutions than in other regions.
Right. And where does your passion actually for autonomous driving comes from?
It comes more from an interest in urban mobility and creating a better life in cities than anything else. I'm really, if you're able to step back and look at today's cities, particularly large cities, it's incredible how dominant the car is, right? How many cars you see, not only driving around, standing still in jams or before traffic lights, but also parked vehicles are everywhere. And it's nonsense, I think, if you would be able to leave that reality and start from scratch designing a city, you would never come up with the city that we live in today. Autonomous vehicles can contribute to more livable, greener cities, and for sure solve the problem of seeing cars everywhere you look around.
Do you mean that the future will look like that there will be a point in time where there aren't any cars in the cities anymore because they are maybe not needed, or because there are so many other alternative ways of transport?
Yeah, I think there will be cars, but when they're cars, they're driving and moving people from A to B, rather than that they are parked or driving empty or are looking for a parking place. I've seen a research that said that 30% of the vehicle movements in cities is vehicles that look for a parking place. So if you would already take out these 30% of the vehicles, it would be a big improvement.
So the notion of digital twin, right, seems to be, everywhere applicable. We talk to Hafniers and like, hey, we want to build this digital twin. We're talking about buildings and okay, we want to have a digital twin of a building, industrial processes, right? It seems to be everywhere in every industry, in every vertical. What is the digital twin notion of autonomous vehicles? What informations need to be included from your side?
So for autonomous, the digital twin is inevitable. There is no autonomous driving without simulation. And the reason for that is that where in today's vehicles, there is always the fallback solution of the driver. In an autonomous vehicle, there is not. So that means that a normal car today with an adaptive cruise control system, cruise control system that remains a certain distance to a vehicle in front in highway applications, is certified with roughly 150 tests on a proving ground. And if the car fulfills nicely these 150 tests, then the system is ready to be deployed on the road. Meaning that for any other situation than those 150 situations, the vehicle relies on the driver to take over. So for any unexpected kangaroo that jumps over the road or object that lies on the road that the car will not see, you rely on the driver to brake on time. If that driver is out of the car and no longer there, it means the car needs to react to infinite number of scenarios, meaning that you need a very different way of doing the verification of the safety performance of that vehicle. And the only way to do that is through smart simulation.
Right. And how would you say is closed loop design related to that? And what does that actually mean?
Yeah, so what that means is that if you run these simulations, if you run, say, 100,000 of virtual runs of different traffic scenarios with different weather conditions, with different road friction levels, with different speeds of the different objects, you will be able to drive up the coverage of testing and come to a conclusion that even by adding more new situations, the performance of that vehicle does not change, is no longer challenged. Anyhow, still there will be accidents. And in real life, we will continue to see new situations that the car was not able to react to safely. And it's that information that you need to capture and need to bring in that engineering process, what we call the closed loop engineering process, such that you can update the controls of the vehicle or potentially even the hardware setup of the vehicle. And then through over-the-air software updates, do continuous performance improvements of the vehicles that are out there in the world. If it would mean hardware, then it's a different situation.
But it means on-air updates, right? This is what you mean.
Yeah, exactly.
Okay.
Yeah, exactly. Mm-hmm. So that's what closed loop engineering is about.
Why is it closed then? So it includes every aspect. So it encompasses all different aspects. Why is it called closed?
Open loop would mean I develop a software stack and I put it in the vehicle and I let the vehicle perform. Where closed loop means that I put it in the vehicle, I monitor the performance of that software stack, I generate improvements to that stack, and I continuously improve also with that the performance of the vehicle. So with closed loop, we mean that the development never stops, that you can even add new features over time. This is what we now step by step see happening in the automotive industry. But that's, for example, already applicable in the agricultural world, where you can buy tractors, like heavy-duty tractors that have a certain performance normally. But if you had a bad weather day and the mud is too heavy and you need to do a very drastic task with that tractor, you can for one day order more power. And then an over-the-air software update opens up all the registers of that tractor and gives you all the maximum power for a day to do that job that you want to do. And it's through these kind of features that you as a car maker, or in that case, tractor maker, are able to have a continuous revenue with your customers, rather than sell your vehicle only once and never see it back again.
So coming back to simulation, so simulation seems to be the core, right? Or at least always part of the progress of in terms of autonomous driving, right? As a vital building block. So how close in terms of, the photorealistic generation, I guess, of data and also applicable scenarios, how close needs to be that actually in the simulation, these scenarios photorealistic, or is there a different modality in there? And can you elaborate a bit of what are these typical scenarios, that needs to be included in this simulation engine? I'm a big fan of, GT, PlayStation driving and stuff like that. And it's like, oh man, it looks so nice. And we've elaborated also in the lab as well as in research, this truck simulator, and we run through entire Europe, right, with the AI engines on maneuvering. And I always wonder, how close needs to be this? And are there typically, you mentioned a couple of 150 tests or something like that? What are these scenarios and what kind of tests do we run through? Can you elaborate a bit?
Yeah, sure. Let's ensure, by the way, that there's no autonomous vehicles in these GT kind of games, right? Then it would be a lot less fun to do.
It is. They're bots, right? I don't know, but we not want to talk about GT, right?
No. Now, when it comes to simulation, so when you say realism, it's typically referred to as fidelity levels, and we need different levels of fidelity at different stages of development. So if you design camera systems, you obviously need a very realistic environment that this camera can see. However, if you do radar simulations or LiDAR simulations, these require very different reflective properties of virtual objects to give realistic inputs from the simulation. So photorealism at certain stages is relevant, but for the massive validation and verification task, that is the key job of simulation when developing these autonomous vehicles. There it is of less importance, and there it's more important to generate realistic inputs for the perception system. And for that, we do not need photorealistic renderings.
Okay, that means perception is like, hey, Unreal Engine, come and go. LiDAR is playing Minecraft. Because we are okay with the concept, and because it's textual, and we're using then the sensor fusion to simulation around that.
Yeah, exactly. What you need to ensure is that the Minecraft output is validated with what the real sensor sees, and we can do a detailed validation works of a model compared to the real world, and compare the outputs from simulation with outputs from the real sensor. And if we manage to build the right sensor model, then indeed you have enough data coming out of the Minecraft blocks for your perception stack testing. And when it comes to scenarios, that's a difficult question. And it's a question that the industry struggles with. There's a couple of sources of scenario inputs. One is, which I think is pretty interesting, is accident databases. And so in many countries, you have accident research teams that drive to an accident as soon as it happened on the real road, and they very detailedly identify what exactly happened, and they generate a description that we can read out in simulation, such that you can put your autonomous driving car in the situation where human drivers had accidents. And then you can see what the performance is of the autonomous vehicles in exactly those conditions. And you can even start to play around a bit with the conditions. What if I do a bit extra speed? What if I had this situation with different weather conditions? So that's one big source. And the other big source is coming out of that closed loop engineering process, is that car makers record data, and they drive around with vehicles on the road, and they see new situations. And we take in these new situations and reproduce those in simulation. But then thirdly, and that's maybe right now the biggest domain of research, is that we can synthetically generate these scenarios. And that by having that simulation environment, you can start off with that accident database or with these recorded scenarios. You start to play those scenarios and identify the domains of interest, identify the scenarios that are actually hard for the self-driving vehicle to tackle, to behave safely in. And in those domains, we then start to generate new variants, additional traffic agents, or with different road friction level, with ice condition, or whatever you can think of. So we start to synthetically generate the critical scenarios that will make the controller fail. And that's, I think, a very interesting new domain of research, because then you can do falsification and you can really challenge autonomous vehicles in the areas where it would hurt most.
That sounds exciting. What role does actually verification play in simulation? Because that seems to be the biggest friction of new mobility solutions, right? So how does that test bed need to look like to be really approvable? And how do you verify this AI system?
Yeah, so there's a couple of items that are really important. One is that the scale that you need to verify the performance of autonomous vehicles is so big that you need test automation. So you need an orchestrator that connects requirements to test case definitions, that translate test definitions in a massive number of scenarios, that somehow also measures coverage of the testing that you do, and that takes in the output of these hundred thousands of runs to digest and to generate insightful representations of that data. So one part is a smooth integration of your toolchain to run massive virtual validation runs or verification runs. The second part is then the closed loop engineering topic that we started off with in the discussion, and that's that you need to ensure that you somehow can add new test cases into that development process continuously, such that you build a kind of learning system that over time improves in its safety performance.
All right. So Matthieu, so vehicles need to move data back and forth and will therefore require to compute more and more. So this also means that cars will become the technical computer hardware for a mobility operating system, which will be the software on the other hand. But what benefits can we expect from this kind of software besides the driving part?
Yeah, a new experience. And I think it's a very interesting stage where the industry is in. I spoke with a system architect who used to design vehicle architectures, a functional description of what the vehicle should be capable of doing. And over the past months, he got the job to no longer look at the vehicle level, but actually start from approach the vehicle as a node in a network. So start with a network architecture in which this manufacturer can add 5 million cars every year that all need to be connected, that need to be able to share information with each other and with the OEM or other interested partners in that ecosystem. So all the excitement we got out of our mobile phones, by the way, also the downsides that come with that connected capability, we will see during traveling as well, especially if you have shared vehicles. The competition will be tough between the parties that offer these mobility services. So the service that gives you the best experience is probably the one that you will choose when you can. So it's exciting, and it's still a big question what it will look like.
Mm-hmm. And what do you think? So if computing will shift more and more in the mobility and vehicle space, do you think that will also affect the chip production? And do we need to shift to a new hardware development technology?
Yes, and that already started. So it's well published that Tesla did the design of their own chip. We see more OEMs considering doing so, starting up activities to do so. The interesting scope of the portfolio that we offer to the industry is that we simulate from chip to city, as we call it. So we have the capabilities to model, to simulate and emulate chip design, system level, sensors, electronics, vehicle dynamics, powertrain, up to city level environments, vehicle to infrastructure communication. And because of that broad scope, that chip to city perspective, we talk with the people that have exactly this concern. We talk both with the chip makers that say, look, what is the spec of the optimum automotive chip, as well as with the OEMs that need these chips and all the different parties in between that try to find their new position in that value chain. So will there be AV specific chips? I think the answer is yes. But will the OEMs be the ones to design those like Tesla did? That's, I think, still a big question for most of the industry players, where, for example, Mercedes announced last year to work with NVIDIA, so to rely on NVIDIA for this.
So you just mentioned the value chain. What role do you think will electrification play in that chain? And maybe also as a follow-up question, will autonomous driving really help us to create a more sustainable future?
If it was not, I was definitely not doing what I'm doing today. So I believe it can. It goes hand in hand with electrification, and it even helps electrification in a sense that one of the big hurdles of electrification is that it takes time to charge your batteries. Autonomous vehicles can obviously, in a much more controlled way, use their battery capacity and ensure that they charge autonomously when there is an opportunity to do so. Of electric vehicles, I think the contribution is obvious, and particularly in a sense that you have no exhausts in city environments anymore, that you need to get the energy from somewhere else is also obvious. But the big gain, I think, comes when cars can plan automatically where and when to drive and just pick up and drop people where they need to be, rather than having people owning their own vehicle, parking their own vehicle, and having all these vehicles standing still in city landscapes.
Yeah, that's crazy how many unused vehicles there are out there and how great actually the potential would be to optimize that.
Yeah, absolutely, and also how big these vehicles are. I mean, typically now it's no longer strange to have one person sitting in a 2,000 kilogram SUV, right?
That's true, yeah. But already now there are like some solutions in cities where there are cars that use like smart paths to pick up people, like taxis. That's already like kind of emerging. But
Yeah,
sure, the
absolutely,
potential would
absolutely.
be.
Yeah, I think we see the boundaries between public and private transport already blurring, step by step. Yeah.
Yeah, right. So Matthieu, it seems to be the hot century challenge. And what are the greatest challenges you think that you will have to tackle in that field? And which role do you think will ecosystems play?
We are at the beginning of a massive disruption of the automotive industry. So the players that have been there for the past 100 years, building combustion engines, more and more advanced chassis systems, they are taken over. They see these disruptors in both in the US but also in China, with smart electric powertrains quickly taking over and approaching the vehicle as a computer on wheels rather than as a premium status symbol for an individual. The big challenge for the industry is to adapt and to not become the Nokia of the mobile phone industry. What my contribution is in ensuring that through simulation can accelerate the development of these vehicles and hopefully also keep the good players in the winning in the front row, ensuring they stay competitive with these very exciting newcomers that, by the way, we also work with. And to make it very specific to my job, so we deliver an off-the-shelf simulation environment, replacing typically homegrown engineering environments. And the big advantage of that is that the investments that a typical level 4 company now needs to do in its engineering toolchain, it can be up to 50 or 60% of the total budget that they have. Whereas if we share that amongst the industry and rely on standardized simulation and test environments, we will be much more cost effective. We will all learn from each other and build in the features that everybody needs desperately. So a lot of reuse, a lot of efficiency gains, and hopefully with that, we quicker can see the benefits of safe self-driving vehicles.
So Matthieu, we see two trends in the autonomy space. Let's say the one is the Waymo thing, right? Which uses also driver-directed cameras, which is an interesting thing, right? And then you have the back of Tesla, which explicitly rather leaves it out. So he, pushing the attention mechanism only on the street and its complexity, right? What is your bet? Will somehow one or the other, recharge their strategy? It's like actually we need to, at least for the transition, to move towards, knowing about the user behavior and what kind of role plays simulation in this driver-directed perception.
So one thing that I think is really important to realize is that the approach of Tesla and Waymo is not only technically different, but also in the way how they approach the market. And so where Waymo focuses on level 4 robotaxi services, Tesla still sells cars to individual people and step by step increases the level of autonomy of these vehicles. And in the end, both could reach a similar business model in a sense that Tesla already predicts that a feature that you can make your vehicle available for others and that other can call your vehicle to use it. So in the end, Teslas will also be a shared resource. But in the challenges to get to that stage, the approaches are fundamentally different. And if you develop a level 4 robotaxi from scratch, I think it's very feasible to take into account that to have an inward facing camera to watch the comfort and safety of your people on board.
Mm-hmm. And if you estimate, so I need to ask a question, obviously, level 5, when will it be worldwide available?
I think level 5 will never be there because level 5 means that you have a self-driving car that can go everywhere. And
yeah.
I think we will not reach a stage where I'm in Leuven can ask my self-driving car to bring me to the North Pole or to whatever. I think that's not feasible. So for me, it will be level 4 for a very long time from now, with just increasing ODDs, as they call it, with increasing operational design domains, step by step. Yeah.
Matthieu, I'm very much into quotes, and one of my favorite quotes is from Samuel Beckett, and it goes like this. So, all of old, nothing else ever tried, ever failed. No matter, try again, and fail better. And I think having a failure culture in place is probably highly important if you work on an ambitious project just like yours. How do you actually deal with setbacks?
Yeah, so my first interpretation of your question was, can we accept self-driving cars making mistakes, causing accidents, and still like them? And I think the answer there is clearly no, right? So we cannot accept a machine to kill people because it wasn't programmed correctly. So there, I think the quote is maybe not applicable. In my daily life, it's definitely applicable. And making faults in simulation is always easy, right? The impact of a fault in simulation is very valuable, I would say. It's an easy learning curve, and the nice thing of simulation is that you can really dig deep into the details of why things went wrong because you have all the information available.
True. And was there once in your life somebody who gave you a really, really bad advice that you that you would like to share here with the audience?
When I was a kid, I always wanted to be a car designer, and I saw myself designing Ferraris and other beautiful Italian cars. And at a certain point in time, I think it was actually myself giving the advice to me that it might not be wise to pursue that dream because, the chance that you reach that is close to zero. But anyhow, since then, for a long time, I should say, I stayed on the path to pursuing that dream and studying industrial design engineering and starting to projects at automotive companies, doing driving simulator research and applying for vehicle design roles at Toyota. My path took a slight curve there, and I think actually into a very interesting direction. So I think just that anybody that advises to take like education decisions or career decisions based on ratio rather than based on dreams is giving the wrong advice. I think there is always ways to combine a rational outcome while pursuing a dream.
Speaking of dreams, right? The good, the bad, the ugly. So we've seen now the ugly. So I don't know, maybe you're retrospective, but you have seen quite experience in in the past how it's pushing automation and daring to dream. Is there any advice or lessons learned you are able to give, young talents maybe, who are willing to try and wants to make a difference in corporations? Are there some best practices you want to share?
Now, so one thing that I see right now is an extreme focus on AI. Even the title of this podcast. I think AI is of extreme importance, but we should not overrate AI. So I would really encourage engineers that want to work on autonomy and self-driving technology to keep their eyes open also for different, maybe more traditional control techniques and perception ideas than just throwing in as much data as you can find to generate an outcome that looks credible. I think we also need a lot of smartness in designing energy efficient, generally efficient ways of looking at the world. Now, I tend to believe that there is not enough attention within the engineering education today to keep that balance correct.
Yeah, agree. There's more than, gradient-based backprop optimization.
Exactly.
Nice.
Yeah.
Matthieu, thanks so much for sharing, and thanks so much for your time today. It was a very exciting session, and yeah, time was really flying actually, and I think we definitely should catch up on this topic. Before we finish this episode, we would like to play authentic autocomplete with you. So let me give you for the closing a couple of sentence starters, and you will just finish. So Siemens is
built on innovation and still going strong.
Beautiful. Autonomous driving is
just a part of the solution that we need to solve in urban mobility.
The world should have more of
people that care about others, people that have less focus on their own well-being alone, but rather look for a balance between their own and others.
Lovely. And last but not least, if I could invent a rule for everyone in the world to follow, it would be
look around and do something with what you see around you. Yeah.
All right.
It's that for me it has been very illustrative time, I think, or in the US, obviously, over the past months. If we don't care about others, then it's just less nice. It's just less fun for all of us. So if we build better cities with autonomous vehicles, then we should also watch around and invite someone else on board when going from A to B and have a nice conversation.
Yeah, that's true. Matthieu, thanks so much for being empathic, very honest, direct, down to earth. I love that very, both the grounding in technology and grounding in having clear views on that. Thanks for spending time with us and your thoughts in this podcast episode. And folks out there, stay tuned. There is so much to come. Stay bold, committed, and open-minded. And we hear us definitely at the next Siemens AI podcast. Thanks, Matthieu.